fourth lecture of this course, which is taking place electronically this time, hopefully not for long. So in the previous lecture, we covered the concept of, just a second. We covered the concept of empty strings and the notion of recognition or accepting. So we say that this machine, this automaton, accepts a language, accepts a string followed by another different string followed by another different string. So the set of all strings acceptable by this language, by this machine, is called the language accepted by this machine. And yeah, we keep revisiting the concept of formal definition of a machine. For example, this machine, which is M1, is expressed as a diagram like this. But M1 can be formally defined using stating its set of states, Q1, Q2, Q3, its set of alphabet, 0, 1, its transition function, delta, which is explicitly stated as a table, or you just state delta of Q1, comma 0, delta of Q1, comma 1, and you spell out every possible answer, every possible state. And you also need to specify the start state, so we can have a single unique start state, but we can have multiple accept states, which are denoted by the letter F. F stands for final states because they accept. And yes, so here for machine M1, this machine M1, the set of all strings, which is known as the language accepted by M1, recognized by M1, it's just all the strings, all the bit strings, zeros and ones, containing at least one, and an even number of zeros follow the last one. So it's okay to end with a 1. If you want zeros after that 1, then those zeros must be of an even number. Just like this, you arrive at 1 here. So you are in an accept state. So you can have a pair of zeros followed by another pair of zeros, another pair of zeros, and that's what. M2 was a machine that is slightly different. It is one state less, but it follows the same, it uses the same alphabet. It has an accept state here. And as we went on, we showed that the language accepted by M2 is the set of all bit strings, and that is the set of all strings, which can be any arbitrary combination of zeros and ones, because those are our alphabet, but they must end with a 1. This is the machine M3, and can you spot the difference between M3 and M2? So this is M2 here. M2 has Q2 as the accept state, whereas M3, make it larger, sorry, M3 here has Q1 as the accept state. What's the first consequence of having Q1 as an accept state? It is accepting no alphabets at all, which means the empty string epsilon, denoted like this, and what language can be accepted by this apart from the string epsilon, apart from the empty string? So 1, 0 is okay. Countless many zeros are okay. And countless many ones followed by a 0, that's okay. So what can you infer?
Anything that ends with a 0 is accepted.
Right, right. So let's move a little bit here to this machine. So this machine here called M4, it starts, I mean, first it has a handful of states. It's got 5 states. It's got 2 accept states. It's got a different alphabet, so it's A, B instead of 0, 1. Not a major difference. But this is just a sequel of what has been discussed. Just have a look at the previous machine, M3. You see M3, and just copy M3 and convert it into vertical, I mean, from this position to this position, so that Q1 is on top and Q2 is just down. And here you have it. Here you have it. And another version there. But you cannot enter the left wing without reading the symbol A. You cannot enter the right wing without reading the symbol B. After you read either A or B, you have the option of accepting. You have the option of rereading more A's or reading more B's followed by an A or multiple A's. And something similar is happening at the right-hand side, at the right side, at the right wing. What do you think? I mean, can you guess a string or the whole language?
Any string that starts and ends with the same element is accepted.
Correct. Correct. So in this example, if you start with an A, you must end with an A. If you start with a B, you must end with a B. So you started with a B and you ended with a B. Anything in the middle can be a completely random combination of A and B. Okay. Let's have a look at. Yeah, I mean, as I told you, we are following the textbook so closely, so you are strongly recommended to consult the textbook, especially for this part of the course. So reading this paragraph can be useful if you'd like to read some illustration why is it the case that you start and end with the same symbol. So let's consider this example. This example has something new. This example here, we have a weird alphabet. So our alphabet sigma consists of 0, 1, and 2, but it has an alphabet. It has something which acts like an alphabet, but it has an effect. So if you read it, something happens. Imagine that as we run this machine, that is, as we read symbols in this machine, we have a counter called sum, which just adds numbers. So let's imagine the following scenario, starting from the start state, Q0. Q0, which has an arrow coming from nowhere. What can I read from Q0? Can you tell me the symbols I can read at the time being at Q0? I mean, what if I read 2? Where does that take me?
Q2?
Right. So here, bear in mind, I can read 2 and go to Q2. I can read 1 and go to Q1. I can read 0 and just remain at Q0. I can read reset. So just treat reset as a single alphabet. I can read reset and would also remain at Q0. But the point is that maintain either on paper or in your mind a sum. It's like a counter which keeps adding the values you read. So starting from Q0 or Q node, yes, starting from Q0, if you read 1, so now we have 1 in the counter. But we moved from Q0 to Q1. What if I read another 1? Where does that take me? Anyone?
Q2?
Correct. So I read 1 and moved from Q0 to Q1. I read another 1 and moved from Q1 to Q2. So we've got 1 and another 1. So please add them. So that would make them 2. While at Q2, I can read 2. Where does that take me?
Q1.
That would send me back to Q1. I've got 1 plus 1 plus 2. That would be 4. What if I am standing at Q1 and I read 2? Where does that take me?
Back to Q0?
Correct. And when you are sent back to Q0, you are sent back to an accept state. And at that time, what's the sum?
6?
Correct. So the unique thing about this machine is that it only accepts if the sum you have is congruent to 0 mod 6. That is, if the sum you have is divisible by 3, is congruent to 0 mod 3. So if it is divisible by 3, if it is a multiple of 3, it would be accepted. Otherwise, it won't be accepted. So what's the meaning of that reset thing? If you read reset, then the sum is reset to 0. It's like cheating. So you just maintain a sum. And I mean, you are encouraged to play with this example on your own. So you can read, for example, if you read 1 and you read another 1 and you read another 1, then you've got 3. 3 is divisible by 3, you are accepted. If you read reset, then you are already 0 and you just reset your 0 to remain 0, you are accepted. If you read 1, you go to Q1, you read 2, you are 2 plus 1 is 3. If you read 1, 3 is accepted. Read 1, you go read another 1, you go to Q2, you read another 2, so you've got 4. You read another 1, you've got 5, back to Q2. You read another 1, you've got 6. Yes, Omar.
So if I go from Q0 and I go to 2, so I go through 2 and I reach Q2, and then another 2 I reach Q1, and then I just go reset. That would make it 4. So 4 is accepted.
No, actually, if you read 2, you go to Q2. If you read another 2, you've got 4, and you are at Q1.
Yeah.
If you read reset would cause the counter to become 0.
Oh, okay. Oh,
so so 0 is divisible by 3.
So it's either a 0 or you go through the 1s until you get a 3. or a 9 or
exactly.
6.
You
Okay.
either read 2 plus 2 plus 2, which is 6, or 1 plus 1 plus 1, which is 3, or 1 plus 1 plus 2 plus 1 plus 1 would be 6. So any combination which would give you something divisible by 3, it would send you back to Q0. Or you cheat and read a reset. You go back to Q0. So this machine is nice and tricky. It is not so tricky, but I mean, it does something more meaningful, at least. Here, I mean, some discussion is put here about this machine and how does it work. So let me show you something. I hope this would work. So maybe I told you about LaTeX and that it enables you to write very elegant documents. Maybe it's time to show you something. Yes, yes, yes. So can you see my browser? I hope. So this is a LaTeX document. To the left, you see the code, and to the right, you see the output. The output is a document. It's a PDF document. So, I mean, the title can be anything meaningful. Introduction to efficient algorithms using probability. And the author can be anyone. Can be, for example, Khalid. Khalid. It's a name which I'm just about to coin. And the date can be, if you want today, you can just write today, or it can be May 17, 2021. Yeah, you have to write make title. Introducing sections is optional. You can write now, you can recompile it to see how it looks like. And yeah, section introduction, and this is an introduction. Yeah, so it would look like this. And I would like to show you this formula, which is the language accepted by that machine, by that counting machine. So begin formula, begin equation, actually, without numbering, please. L of M3, and I would like M3 to appear like that, equals W in 0, 1, 2, and that would be raised to the power star such that sum, and that sum begins from I equals 1 to the length of W, and that would be all the strings which are equivalent. I mean, you can write text like that, divisible by 3. If you run it, I mean, just look to the right. We've got some errors because maybe I didn't include the package. Use package AMS math. Yes. Yes. Now you can see that this is how the equation would look like. Yeah, of course, if you've got some integrals, if you want to write some integrals, you can write something like that. Begin equation. If you want the equation to be numbered, so for example, int from 0 to 1 e to the x dx. So this is how it should look like. So I hope you've got impressed by what you see. This is LaTeX, and this is how it looks like. This is LaTeX, which was developed, which is based on tech. You see the output. So now you saw it once in a lifetime. I hope, I mean, you like what you said. I hope you get to appreciate what professional typesetting means. So this entire book, by the way, was generated using LaTeX. And you can make drawings, you can make slides, you can make theses, you can make books, you can make reports, you can make posters, and you can do a lot of things. But yeah, there is a learning curve. So that was the expression of the language I wanted you to see. And by the way, just let me show you more stuff. I mean, just to elaborate about what I have. Just to elaborate about what the language is accepted by this machine. So languages or strings accepted by machine. Machine is misspelled. Machine by machine M3 are begin itemize. So 1 2 1 1 1. Can you suggest another string? Anything that sums to 3 or a product of 3. I mean, a multiple of 3. 2 1 0 2 1. So those are all accepted. See how they would look like. And on the other side, rejected strings. Rejected strings, and there is a nice text handling stuff here. You can delete the whole stuff here. So 2 0 0 1 0 1 1 1 0 1 0 0, if you wish, or just 1 2 1. Countless many strings. 2 1 1. that would look like this. Okay. By the way, that was not M3. Let me fix that. M5, and we can fix that all over the text area by this. So it's M5, it's not M3, just not to be confused. Yes. Okay. What I would like to tell you is that, do you see this? Do you see this sense of accepting or rejecting? It's very man-made. It's just completely designed by a human effort. And what you see here, despite its simplicity, it captures the very essence of computation. So some computation happened here. We recognize the number that is divisible by 3 or not by designing a machine, by designing an abstract machine, a very simplistic abstract machine, which has very little memory. So we are testing if a number is divisible by 3 by maintaining very little memory and having a few states and a simple transition between the states. Yet the task is not bad. It's not bad. We're doing something that is not bad. This is the very essence of computation. This is the very, very essence of computation. Although we can introduce improvements to this model of computation, what you see here, I mean, this machine is classified as a finite state automaton. Sometimes we call it deterministic finite state automaton. Sometimes we call it deterministic finite acceptor, or just a finite state machine, or an automaton. Altogether, this is called the model of computation. So please accept the fact that, I want you to be convinced that accepting an input, being able, by this model of computation, by this machine, being able to classify inputs into acceptable inputs and rejectable inputs, accepted stuff and rejected stuff, is by itself the sense of computation. So this is computation. We are either accepting things or rejecting others. You can, of course, introduce improvements to this machine. And by the way, remember that this machine, this representation of the machine is very graphical. You can see the machine, but we can introduce more description to this machine so that it's very hard to draw or even impossible to draw. Yet it is still a finite state machine, but can be only described using notations, using definitions. And we will be having one in a minute. So the machine here, M5, accepts all strings where those strings, strings of zeros, ones, and twos, and maybe reset is included. Reset can be included. It's like cheating, but zeros, ones, and twos, where the sum of digits within that string is divisible by 3. Can we modify it? Can we modify it so that the sum is something else? Well, the answer is yes. We can modify it. At least we can modify it by definition. But drawing it can become tricky. Can we introduce the parameter I so that it accepts only strings of alphabets which sum to I, strings of digits here, which sum to I, or a multiple of I. So that's why here the textbook introduces this discussion that consider a generalization of example 113. 113 is that example here, which has a figure 114, And then comes the example 115 to talk about example 113. Using the same 4-symbol alphabet sigma. For each I greater than 1, let A sub I be the language of all strings, where the sum of the numbers is a multiple of I. So in our example was a multiple of what? Can you recall?
3.
Correct. Except that the sum is reset to 0 whenever the symbol reset appears. For each AI, we give a finite automaton BI. Recognizing AI, we describe the machine BI formally as follows. So this is how the machine is described. It's not the most beautiful highlighting. So this is how the machine is described. Here, we've got a set of states, a set of alphabets, a set of a transition, but some transitions, a start state, and a set of acceptance states. And that would be only one accepting state. And that needs to be the first state. But what would change is that here we have where Qi is the set of I states. Those are the I states. And we designed the transition function delta I so that for each J, if BI is in Qj, that is if the machine is currently in that state, Qj, the running sum is J modulo I. This is just a verbal statement of this rather tricky machine. So you don't need to bother a lot about it. I mean, we are just communicating an essence, an idea. And this is how it would look like. But let's move to the formal definition of computation. So what is computation? Computation means that we have a machine which can accept and can reject. In other words, it can classify. So let's read this paragraph. So it tells you that we informally defined what is an automaton by drawing. Then we formally defined what is an automaton by giving you the tuple, the 5 tuple, which is sigma, the Q set and the sigma set and the transitions, the start states and the final states, the single start state. And yeah. So here we already have an informal and we have a formal. Let M be this machine. This is a finite automaton. And let a string W, which consists of the following sequence of alphabets, let that string be input to the machine. So for all W1, W2, Wi, until you reach Wn, all of those are alphabets within the set sigma, and those are currently being read by the machine M, causing machine M to move from one state to another through the transitions. When do we say that machine M accepts the string W? We say that if you start with the starting state, and one transition after another lead you to one state after another until you reach the state Rn. So we call the states R1, R2, R3, R4 until you reach the state Rn. When you reach the state Rn, Rn is an accepting state. So that would be the case where machine M accepts the string W. And in that case, we say that what if machine M can read other strings apart from W, like W to the power 1, W to the power 2, W to the power 3, or countless many other strings, and they can classify it as accepted. So the set of all accepted strings is called the language of that machine. We say that, as we say that M recognizes this language, it means that we have a computation here. So machine M is doing a computation, and its computation is recognizing that language, recognizing all strings belonging to that language, and of course, rejecting all other strings. If the language is accepted by a finite state machine, like the ones we had so far, not by another more advanced model, then we say that this language is a regular language. So what is a regular language? It's just if it's a language that is recognizable by a finite state machine, finite automaton, deterministic finite automaton, because later we will be introducing non-determinism. And by the way, non-determinism would still cause the machine, the language, to be said regular, to be described as regular. But yeah, non-determinism introduces some different challenges. Yes. What do you think of this string here? Recalling the machine M5. What about 10 reset, 22 reset, 012? Let's go back to the machine. It's done. Let's read one. One would take me from Q0 to Q1, followed by a 0, I am still at Q1, followed by a reset, I am back to Q0, followed by 2, I'm going to Q2, followed by another 2 going back to Q1, followed by a 0 still at Q1, followed by a 1 going back to Q2, and then 2 back to Q1. I forgot to do a reset here. We've got 2 and another 2 going back to Q0. Let's do it again. Starting from Q0, reading 1 would send you to Q1, reading 0 would keep you at Q1, reading a reset would send you back to Q0, reading 2 sends you to Q2, another 2 would send you to Q1, and another reset sends you back to Q0, followed by 0, you are still at Q0, then 1 going to Q1, then 2 back to Q0, you are accepted. Yes. And this would trace the states through which the machine passes. Machine M moves from Q0, Q1, Q1, Q0, Q2, Q1, Q0, Q0, Q1, and Q0. So this satisfies the 3 conditions, which means that this is accepted. And that would lead you to the sum, the language describing all the strings accepted by M5. So W such that the sum of the symbols in W is 0 modulo 3. This is a number theoretic term, so it means that it leaves remainder 0 when divided by 3, except that reset, I mean the symbol reset, resets the count to 0. So it's a regular language. Designing finite automata, maybe we can discuss that in an upcoming lecture. Inshallah, that would be face-to-face. Okay. Any questions? Well, I hope you're doing, I mean, you were keeping track, we're following. Okay, good to have you today through Teams, 20 of you. And see you next time.
يعطيك العافية دكتور.
الله يعافيك.
يعطيك العافية.